Alright, welcome back everyone. So, we are talking about quantum Hall effect in a lattice with a magnetic field. So, we talked about a two-dimensional lattice and a square lattice with a magnetic field that is perpendicular to this two-dimensional space, and what we found, what we showed is that through parallel substitution, earlier we had this being our unit cell, and now because we have a magnetic field and vector potential depends on position coordinates. So, momentum are no longer a good quantum number. Then we made a choice about the gauge, made a gauge choice in which we can make a magnetic unit cell of length p along x direction and the same one unit cell along y direction. It is a choice, and you can make even a square one if you like by distributing a tilde and b tilde equally, or even a rectangular lattice, but this is a choice that makes it easier for computation. And when you make a choice in the gauge choice, then you can also argue that the band structure you are going to get is also depends on the choice. So, the band structure you are going to get is not really observable, but the essential salient properties of the band structure, band gap and any property that we obtain from the band structure including topological invariant will however be a gauge invariant one. Okay. And here we made a choice saying that we will make a magnetic unit cell of length p times the original unit cell such that the flux is integer times flux quanta, right, whereas the flux then per unit cell is of course the flux divided by p, because this one made of p unit cell, and that gives us this quantity. Now we can, because this is a magnetic unit cell that repeats everywhere, so this is the magnetic unit cell that repeats everywhere. It is called magnetic unit cell, or we can also call it supercell. Okay, mathematically they are the same thing. So, then we will have the kx. So, the magnetic unit cell when it increases by p times, so the Brillouin zone should reduced by p times, and that is what the reciprocal lattice vector does. So, we just increase the length of the unit cell by p times. So, your magnetic unit cell has reduced by p, okay, whereas along y direction it remains the same. So, this is the reduced magnetic Brillouin zone we will get. Okay. And earlier we had one electron per unit cell and one band. So, now we have p electrons or p atoms per unit cell or p bases per unit cell, and you should also get p bands, and this will be very similar to the chronic Prenny model or near free electron model, in which how we fold a parabolic band into a unit cell, and then that opens a gap at the magnetic zone boundary. Now, what we are doing is that we started with a band, and I have drawn that band earlier and I will draw it again, which was going from 0 to 2 pi by a, but now at 2 pi by p a the band will start folding. So, I started with a band or folded band, and now I am folding it with a smaller size. Okay. And so, this is how it will be. I started with some band which was minus pi by a to pi by a, and now this is my new Brillouin zone. So, what will happen is that these things will now fold back. How many times? Q times, p times, because this is reduced by p. and every time at this point, now this is my new Brillouin zone boundary, and there will be a gap opened. That gap will open by the hybridizations along the x directions. That is what we want to establish. Okay. And there will be lot of indices, and so you just go through it carefully, and here we will do a little faster, but you can go through it slowly by pausing the video and see it. As we said, so this is my unit cell now P, and now in this unit cell now, and actually this is my unit cell, okay, or magnetic unit cell. So here the hopping is T, here the hopping was T, and okay, the way this is defined, we start from here. Okay. Recall the fact that at 0 there is no chiral phase, whereas here there is a chiral phase which we denote by phi, because the total flux is here 2 pi, or the total flux is q times phi 0, but that we have divided by p times. So, every unit cell now, the smaller unit cell now has flux of flux of q pi by p, and that is what we denoted. Phi we denoted by p by q times 2 pi, that is the phase, and this is just a constant, right, e to the power h by e, and the actual phase is e by h phi 0. So, that becomes E, you might not be able to see. So, phi by putting all these E by h and getting 2 pi here, that is the phase. So, each one then has a phase of 2 pi, phase of phi, right, as the electron hops from here to there. Okay. So, now what we do is that we have p number of atoms per side, and every atom has 1 electron. So, now we have to increase our Hilbert space to p times. So, C1 here correspond to the first one, C2, C3. Now, this I is a tricky I. It is actually now this is the I, and this unit cell will be I plus 1, and this one will be I minus 1. This I now corresponds to magnetic unit cell index, and each unit cell then we will have 1 to p electrons. Okay. And along ky direction, we have not done anything. So, the periodic boundary condition remains intact. So, along y directions we will keep using ky. Okay. Only along x directions we just have to expand the Hilbert space. And the second one we said that, and we showed it earlier, that there will be a chiral phase, and that we just added to e to the power I k y plus phi. That is what this notation means, and we keep adding all the way to p minus 1, right. So, the total flux is phi. All right. So, this will be then the Fourier transformation. If you want to go back to entirely real space, and here n would denote this index. So, kx, ky, but remember now the kx is defined from 0 to 2 pi by Pa, whereas ky remains the same, and this is how the reciprocal lattice vector will look like. So, kx times xn and ky plus n plus 1 phi ky. Okay. I think it is all right. This entirely is replaced by this. So, that means there is still a I. So, now if you do that, we had a summation over ky, because we are in the Fourier space along ky, and the real space one we are going from I equal to 1 to, this is the magnetic unit cell. So, earlier we had n number of unit cells, now we will have n by p number of magnetic unit cell, and then we will have a summation over per magnetic unit cell we will have a summation over I equal to 1 to p, that is the number of electron. So, this is still in the Fourier space. So, this is the hopping now, because hopping now depends on ky for each side, going from n to n plus 1. Okay. So, it will be like this. So, and the second one will be like this. Along this direction I have already taken e to the power ky. Okay. So, this will be the dispersion now. But now you will have a dispersion which is ky is still a good quantum number, but now you will have p number of bands, n goes from 1, okay, 1 all the way to p. So, you will have p bands. Okay. The rest remains the same. So, it's better to just work this out, the intermediate steps, and you should be able to obtain it. So, now what do we do? Generally, if you have, it is like a p orbital, p number of orbitals if you like. So, there will be intra-orbital n to n, which is from n to n this way, right. This is the nth, or this is the first one. So, the nth one will be somewhere here. Along this direction, it is the hopping between nth electron, whereas from here to here. So, this is the first orbital sitting, this is the second orbital, this is the third orbital. So, along this direction it is n to n plus 1 hopping, n to n plus 1. So, this terms, whereas along this direction so these are going to be in the diagonal. Now, what do we do is that we make a matrix. So, we will have a p by p matrix per magnetic unit cell, or p orbital. So, it is a orbital p by p orbital Hamiltonian, and this is what we wrote. Okay. C1 all the way to Cp and this way. So, these are the diagonal terms that comes from this term. So, we and whereas the hopping from, sorry, this one should be T. Okay. So, the hopping from here to there still remains T, sorry, from here to here remains T, this one is already included. And this is the hopping term. There is no third nearest neighbor, we have not included the hopping from here to there, this was 0. You can generalize it to second nearest neighbor hopping, and you will see that how things changes. That will be a good interesting point. But now there is one interesting thing, from here to here there is no hopping, but recall that this point, let me use a different color. Not too many colors are available. Okay, I will still use this. So, this and this are same, right. So, hopping from here to there is like a hopping from here to there, and that is the periodic boundary condition. Because of periodic boundary condition, one gets this. So, that means once we lift the periodic boundary condition, this is an homework for you to do, you do not have this phase anymore. I mean, you will have it, but not with in terms of the k, due to periodic boundary condition with a phase of k, kx. I think we might call it kx tilde, because this is a tilde. Right. All right. So, then we started with a band from minus pi by a to pi by a, which are written here in the original band, one band we had. And now our unit cell from minus pi by p a to plus pi by p a, right. These are our g tilde. Along y direction it remains periodic. So, along y directions the band structure will remain the same, it is only along the x direction, and that was the choice of the gauge. So, now this becomes our reduced Brillouin zone or magnetic Brillouin zone. It is folded. So, how do you do that? We take this part and it has to be continuous. Then we take this part, again we use red color here, this part, and then we will again fold it like this, and we will have such piece p times we will fold, because here from here to here you will have p times, right, from here to here. So, we will have p such band, and what happens here when they meet? So, what I have done is this one, I have just plotted this one, this was the original band structure and I have shifted this. So, I am just plotting, so far this is our E k plus phi, and then this is E k plus 2 phi all the way to p phi. But there is a hybridization between them which is due to the hopping along the between the interorbital hopping, this hopping. What it will do is that it will open a gap. Okay. It will follow like this and it will start bending here. And then the other one which we folded here, it will be exactly this sort of folding and not just meet here, this one was supposed to be folded like this, but then it will open a gap by T. Okay. And here also, when this one and this one, this is the point I was trying to draw here, this is the point, and then again opening T. Okay. Write a small code to do this and you will see that these are exactly how it is coming out to be, and those are the P bands we have drawn. 1, 2, 3, 4 all the way to P. We started with one band, now we get P bands because we are in the reduced Bernstein zone. So, number of electrons has not changed and all, it is just that all the electrons which were outside and the chemical potential was somewhere here, they are now gone into this magnetic zone. And they are supposed to be same, and my drawing is not doing that. Okay, they are okay, they are supposed to be same. They are exactly the same point. All right, and there will be P such band. So, these are actually nothing but the Landau labels which was denoted by N earlier, which are now become P number of bands which has a dispersion because of the lattice, the periodic boundary condition. So, you can actually compute it and you can even plot this as a function of magnetic field, and the way we write magnetic field is here through in terms of flux. As you change magnetic field, you change flux, right? And as you change flux, your magnetic increases and you write the bands. How many bands? P bands, and the number of bands will also keep on changing, and you get patterns which are like this. energy levels. This was done by Hofstadter, and I gave you the reference called butterfly. So now we had a Landau quantizations, the flux quantizations per band. Now we have a P band, and what is the quantization? And if you do this, you have this band structure. Now if you compute the quantum Hall, the Hall effect, you are supposed to get quantum Hall effect, which we are supposed to count how many such bands are filled at a given Landau levels. And then as you change the increase the magnetic field, your flux increases, so number of band increases, and so and the unit cell also the unit cell becomes larger, but your magnetic zone reduces. So there are supposed to be more folding. These bands will again fold after you change an unit cell by after you increase the unit cell by one more, which to include one more flux, right. As you increase one more flux, then you increase the unit cell and you reduce the Brillouin zone. So once you reduce the Brillouin zone, then again more bands will be folded back, okay. And then depends on the chemical potential, so the bands will be filled or empty, and then you will have a change in the quantum Hall effect by removing the band from the Fermi level or filling the band by the Fermi level, okay. So this analogy is fine. It's you can also see it numerically, but what is more interesting and why the TKNA number is more famous is because they computed quantum Hall or Hall conductivity and showed that they are related to Chern number. Okay, we really have not introduced what is Chern number, but let's at least see the calculation and see what could look like a Chern number. Okay. So for that we use Kubo formula, and any textbook will give us these are the number of atoms or number of K points, and then we have Kx tilde Ky. We also have a now P number of bands, right. So we will have this is a calculation that you need to look it up or do it yourself. So let me introduce K. This is the numerator. So the numerator will be eigenvector of that P by P matrix the velocity along kx and kx tilde and the same thing along ky and of course then for both case and here, so there will be a kx goes to ky plus or minus, actually it is minus, it is important. This is the velocity of or band velocity along the x directions and band velocity along the y directions. So, these are now you can start recognizing that this is like a derivative along x directions in the momentum space, this is like a derivative along the y direction, and then there is a minus y direction derivative and x direction derivative. Okay. And we will do this more carefully in the next chapter, but what one can do is that this sort of term and the other one can be converted into, and there is a denominator with energy with a Feynman-Hellman theorem in which the derivative of the Hamiltonian by using the time dependent Schrödinger's equation we can convert into the derivative of on the state. Rather I can even do it this way, both are equivalent because of hermeticity. And then there is a summation over m, and one can use the completeness to get rid of these states, and what you will eventually get because of minus with x goes to y, you will get a cross product with this, and there are all these summations and n and m and k, all these things are there. So only the k would remain. And you can in fact do it this way. And we can call it a vector potential like thing, but there is no, I mean this is just the definition. So, then this will look like and recall that this is like curvature for nth band. And this k summation, if you have a large enough system, the k, the separation between different k are small enough, so that we can make an integration over k over this entire Brillouin zone for n, a magnetic Brillouin zone. So, this is our now if I call this Cn, so I will have so this is a quantity that we will identify to be Chern number which is just the Berry curvature summation or integrations over the entire volume or the Brillouin zone area. So, it just tells you how many bands we are filling, right. So, it remains integer, and this one is also will show that it will be integer. So, it just tells you how many bands we are filling, and we are not computing anything else in the band except a topological invariant of each band, and that is why you get a integer Hall effect. Homework: use a magnetic field so that you have only 2 unit cell making of the magnetic Brillouin zone. So, one should be able to obtain a Hamiltonian which is a 2 by 2 Hamiltonian, it is like a 2 orbital, and you will have ky plus phi t e to the power I kx by 2 t e to the power plus I kx by 2, and one should be able to write it in terms of d0 dx sigma x plus dy sigma y plus dz sigma z, whereas sigma 0 is identity and sigma x y z are the Pauli matrices. Not in the spin basis, but in the orbital basis. There are 2 orbitals here, and you can work it out what they are, and it is sort of important for you to figure out what they are, and you will see that this is, you will get a Hamiltonian which will be very similar to a Chern insulator Hamiltonian that we will introduce later called Rice-Miller Hamiltonian. Okay. And we will compute the Chern number and everything exactly, but you can just do this calculation here. You can just diagonalize this Hamiltonian and obtain the eigenvalues and eigenvectors, and you can go and compute this and also this, and you can plot those. You can write a small Python code and you can plot it, and you will already have all the answers that you need before even formally introducing Chern number and all. In the last part, we will talk about quickly the boundary and edge modes, and again this is something that you should do numerically. Modes or states. Okay. So, we had some magnetic unit cell, there are many such atoms in between. Now, what we will do is that let us not put the periodic boundary condition along y direction. What we generally do is that when we put the periodic boundary condition, we say that at the end of your material, this side and this sides are same. So, you sort of make it a torus, but we will do the torus along x direction, in which this is some p number of, and then you will have more outside p number of atoms in a magnetic unit cell, but along y direction we will not put this and this atom to be the same anymore, they are different. So, let me even color them. So, these are, and this is called open boundary condition. Y. Okay. And along this side you will have different. So, let us consider let me actually anyway we can draw, let me see which one is drawn. Okay. So, this was the band that we obtained, okay, and they are supposed to be particle hole symmetric. So, that means this band and this band are just completely opposite. My drawing does not do that. So, here some n is equal to minus of m. So, for every band there is a minus of that, another band is a minus of that band, that is what the particle hole symmetry is, and you will see that it will indeed do that. So, this band and this band are supposed to be just plus and minus of this, okay. And this is, and there will be many such band, p such bands. But now what we have done is that we have now removed the periodic boundary condition between these two. So, they are no longer the same atoms. Okay. So, ky is no longer a good quantum number. So, now even each band will split into many bands with hopping roughly is of the order of t along y directions. So, this is happening along y direction, this splitting is happening along y direction. This is still along kx direction. This is minus pi by Pa, this is plus pi by Pa, but along y directions we removed it, right, and these are called quantum well state. Okay. And these are how the states will split inside for all these atoms. There are many such atoms and there was a T hopping because we lifted the periodic boundary condition. So, these bands which was a band earlier now will all split into how many bands? Ny number of bands, bands which we will call quantum well state. So, what will happen to these states? It will be very surprising to us and we will not be able to show it. You can probably do it for a 2-band case. It is a good exercise for you to do it, and we will do it in a later on. But what will happen to our surprise is that at the end there will be a metallic band that will go from. So, this sort of band at the edge will become like this, and so there are also this, but there will be only one state, and this the other band, there are p band, that will also have another state. So, there will be again another band from here to here. So, there will be such and so on. So, p number of H states. What that p is coming from? There are p orbitals, right? P orbitals. Each one will have a metallic state. Now, what will happen here? There is also periodic boundary condition is lost, and it will also be surprising to us that they will be however localized in the other direction, this direction. Okay. And they will be dispersing like this way. And they will pass through Fermi level. So, metallic H state. You see, in one side it goes to one side with a velocity that will be like a Vx will be, let us say, negative. In this side Vx will be positive, which would mean in this side Vx is negative. So, they will be going this way, the currents will be along this direction, whereas in this side Vx will be positive. So, there will be current along this side. There is a metallic system. Okay. So, even for bands in a periodic boundary condition, we reproduce the same result that we obtained through Landau levels by tilting it with the confining potential. Here is also confining potential, which we did by turning off the hopping from this side to this side. Hopping means there is a finite probability of electron to hop, but now we said that because it is kind of a infinite potential here, the electron cannot hop anymore to the other side, which was supposed to be this side in a periodic boundary condition. So, conceptually they are the same thing, but mathematically we are doing it in a different way and we get the same result. Okay. And this was the beauty of TKNN, which gave us the first intuition that the quantum Hall effect is also nothing but topology. So, this is the end of this chapter. In the next chapter, which will be from the next class, we will start introducing Berry phase, Chern number, winding number and so on without magnetic field. Now, we got an idea that all these calculations in which we had this magnetic field, but we sort of played around the magnetic field by making the magnetic field is included in these calculations by making the lattice larger and then introducing some phase, okay, making the lattice larger. So, that means now if I have a large lattice, that should already have this Chern number and Berry phase and Berry curvature without necessarily having a magnetic field, if I have some sort of a phase coming from somewhere. So, that is what we will learn from next chapter. All right. Thank you very much for your attention.